Okay, so we are going to demonstrate a transverse wave and a pulse. The first thing I'm going to do is a pulse, which is just a quick flick of the wrist. And you can see that the wave traveled in that direction to the left and then came back on the right. What you should have noticed is it wasn't as big when it came back as it was when it went. And so that is just because of energy loss due to the friction between the coils and the tile. Next, we're going to do a transverse wave, which goes up and down. So you can see it going up and down, and you can see the top part is the crest, the bottom part is the trough. And if we just let it come to a rest, this represents the equilibrium position. We have two types of wave. I just showed you a transverse wave. There's also a longitudinal wave, and we're going to talk about the function of wave. We already mentioned it on the energy. The function of a wave is to basically transfer energy. And when I did my pulse, you could see that the wave I produced and the wave that came back, they weren't the same height. So that means it lost energy. Now the transverse wave, this line here represents the equilibrium position that I talked about. You have the upper point, then you have the lower point. This right here represents a crest. This right here represents the trough. If I was to keep going, this would also be a crest. The height from the equilibrium position to the crest, or from the equilibrium position to the trough, represents the amplitude. Now the amplitude represents the amount of energy in the wave. It is not a direct relationship, but if you have a bigger amplitude, you have more energy. We also need to talk about a wavelength. A wavelength is one point to the consecutive wave, the exact same point on the next consecutive wave. So it could be crest to crest, could be trough to trough, it could be from this point to this point, or this point to this point. They all represent a wavelength. Okay. Now the period is the time it takes for one wave. So if I was to label this, this would be one period. That represents the time for one wave. Frequency is the number of waves per time, which you figured out in the speed of Sound Lab. So this would be a half of a period. Okay, so the definition of a transverse wave is that the medium moves perpendicular to the direction of the wave travel. So in this example, the wave is moving in this direction, and so the medium is moving up or down, which you'll see more clearly when we do the wave grill in a minute. Now we're going to demonstrate a longitudinal wave. And a longitudinal wave means that the particles move parallel to the direction of motion, unlike a transverse wave, which was perpendicular. So if I create a vibration, you can see that it traveled in the same direction that the wave moved. You can see areas that are compressed, and you can see areas that are spread out as it travels. Okay, so what we're doing here is creating a longitudinal wave, not just a pulse like last time, and you can truly see the areas where it's spread out and where it's compressed. And there's another compression on that side as well. Okay, so longitudinal wave, the particles move parallel, and so when we draw a longitudinal wave, we draw areas that are compressed, and we draw areas that are spread out. So the areas of compressed are actually called compression, and the areas that are spread out are called a rarefaction. A wavelength is still from one point on one wave to the consecutive wave, the exact same point. So you can have a wavelength from the beginning of a compression to the beginning of the next compression. You could do end of the compression to the end of the compression. So whichever one works as well. A compression is the area of high pressure, and refraction is an area of low pressure. Okay, so what we have here is a wave grill, and we're going to use this to demonstrate reflection and interference. What I want you to notice is that the short are here. We have a transition piece that goes from short to long, and on the right side there we have the longer bars. So now we're going to set them flat and give them a second to rest. And what I'm going to do is create a pulse. And when I create the pulse, you're going to see that the medium travels perpendicular a lot better than you will with the slinky. But I'm just going to create a pulse on this side. And as it travels, you can see the pulse move. And you can see that this medium moves up as the wave is moving in that direction there. So the first thing it asks us to look at in the wave pulse is the wave speed. So where is it going to travel faster? So if I create a pulse in the middle, and you're going to watch to see which end it gets to first. Okay, so which end did it get to first?
The left, the short bars.
Okay, so it got to the short bar first, and I'll go ahead and do it one more time in case you missed it. You can see it got there probably when this one had only traveled about half to a third of the way. So the short bar has a greater velocity. Okay, now, next thing they asked us to look at is the wavelength. So I am going to actually create a wave instead of just a pulse, and I want you to see where the wavelength is longer and where the wavelength is shorter. So, where's the wavelength longer?
The left, the short bars.
Short bars are definitely longer. So here we have a longer wavelength and a shorter wavelength on this side. Now, what's controlling the wave when I made it?
You are.
I am, and that wave is being controlled by me, and that I am basically the generator. I am the frequency generator. I am controlling the frequency. So is the frequency changing?
No.
No. My hand is moving up and down at the same rate, which means that even though it's changing as it moves here, not the frequency, but the wavelength is changing and the velocity is changing, the frequency does not change because that was generated by my hand moving up and down at a constant rate. So frequency stays the same for both the short bars and the long bars. Go.
So, Miss Wolf, what determines the frequency of a wave?
Right now, what determines the frequency is me, which is the source. So whatever the source is what's producing the frequency of the wave.
Okay. And then what determines the velocity of the wave again?
What determines the velocity is the medium. The medium in this case is the wave grill, but if you remember from the beginning, the wave grill had shorter bars on this side and longer bars on this side. So the medium is changing. It's even changing through the transition piece because you've got more bar here because it's a longer bar and you have less of the bar here. So we are getting a medium change. So the medium changes as it moves in that direction, which means the velocity changes, the wavelength changes, but frequency will remain the same when it changes mediums.
Okay, so as long as you keep pushing up and down the same rate, the frequency will stay the same.
Correct.
How could you change the frequency?
By going faster or slower.
Okay. Ooh, those are cool. That's a standing wave where it just looks like it's going up and down, even though we know the energy is going left and right.
So we are going to demonstrate reflection. There are two types of reflection. There's a fixed end reflection, which does not allow the medium to move, and a free end reflection, which does allow the medium to move. So we're going to do a fixed end reflection first. So as you can see, as it traveled along, the pulse was up, and then when it hit here, the pulse traveled down. So the pulse flipped sides. It was on top, then it went to the bottom. So we'll go ahead and do it again. And then you can see that it stayed down. And that's a fixed end reflection, and we say that it flips. It's up, down, or it's down and then it's up. We also call that a phase change. Okay, now we're going to do a free end reflection, which means the medium is free to move. So again, I'm going to generate a pulse. You can see it was up and it stays up. So there's no flipping. I'm going to do it one more time. So it's up and then it stays up. So there's no change in phase. Counter reflection, which basically means to bounce off. We have our fixed end reflection. So as I said, the medium does not move with the wave. It flips, and you have a phase change. So what does that look like? If I was to draw a pulse traveling in that direction, here is my fixed end. When it comes back, it's going to be traveling down and to the left. For a free end reflection, the medium is free to move. It does not flip. And there is no phase change. So what does that look like? Again, you're going to have your wave pulse traveling that direction, hits a free end, and that means it's going to still travel on the upside, traveling to the left. We are going to demonstrate constructive interference and destructive interference next. So for constructive interference, we're going to send the pulses in the same direction, and you need to watch and see what happens. 1, 2, 3. So they met pretty much right in the middle, and you should have seen that the pulse got bigger. So I'm going to do it one more time, make a really big one. I'm going to do a really smaller one because I want you to see what happens as it travels as well. Go. So what you should notice is the big one kept traveling and the small one kept traveling in this direction. So they don't bounce off each other, they travel through each other.
Let's do that one more time.
Okay, we're going to do it one more time. 1, 2, 3.
Big keeps going down there and I get the small one.
Yep. So you can see that the waves travel through each other. They do not bounce off each other. Okay, next you got destructive, which means the wave pulses are going to be in opposite directions.
I'll go up.
Okay, 1, 2, 3. And what you should have seen here is instead of when we saw it get bigger with constructive, you should have seen it get smaller where it met up, and you should still see the bigger pulse traveling in this direction and the smaller pulse traveling in that direction.
Let me go down this time. Then I can be bigger.
Okay,
You
1,
go up.
2, 3. Okay, so we're going to talk about interference, and the first thing that goes with that is the law of superposition. It's basically just the algebraic sum of 2 or more waves. Now, there's 2 types of interference. There's constructive. You can think of these as being added together. They're in phase, meaning they're in the same, either up or down. Okay, so we are going to draw a picture of the constructive interference. Remember, these are going to be in phase, meaning they're going to both be up or both be down. So I'm going to draw this one up, and it's going to be 2 units tall. And I'm going to draw this one also up, 1 unit tall, heading in the opposite direction. So these 2 wave pulses that will generate, when they meet, they will be 3 units tall. And then afterwards, the 1 unit is going to travel in this direction, and the 2 unit will travel in that direction. Next, we have destructive interference. So for destructive, they basically subtract to get that resultant wave. So this would be crest to trough or compression to rarefaction. And so when we draw it, we're going to have a 2 up. And let's say we have a 1 down. The 2 is heading to the right and the 1 is heading to the left. So when they meet and overlap, it's a subtraction. So 2 minus 1 gives us a 1. And then they're going to keep traveling in the same direction they were traveling. So the 1 is going to continue to the left and the 2 is going to continue to the right.